Yeah, see, it's an important risk for this in the malware analysis class. If you have a vulnerability inside a virtual machine, then in principle, it's isolated to some extent from the host, but that is not perfect. So certain attacks can crawl from the VM into the host, especially now because of Spectre and Meltdown. They had that effect. Virtual machines could crawl out of the virtual machine and attack the host or attack another virtual machine on the same host.
I can see that. Okay.
And also, they can do a network attack.
Yeah,
so an infected virtual machine could affect other machines on the network. So these things are called VM escapes when they get out of a VM. And they happen every now and then. They are not very common. So most people continue to figure that a VM is safe enough, but it's not perfectly safe.
Well, that made me think more once I was able to, on the host side, and I tried it on the Windows side too, just for the curiosity. And, you know, I'm able to get into the real world. But if that's the case, then I'm opening myself up.
Well, if you run a vulnerable VM, or a VM with, say, an open listening port, then that means people can connect to the virtual machine and use it if they can get on your network. If you run in that mode, in VMware, then they can't get to you because there's a router in the way, virtual router. So the risk is not too bad. If you connect to a real network, anybody can use your machine. This is project 3 and 4 due today. I just made this last scheduling on 9/29, no class. I will be in Arizona. All right. Anyway, it is, and some people say this is why you may notice Kali does not have SSH on by default. And if you turn it on, they want you to use a certificate, not a password. We had to lower the security twice to use it over SSH. So if you are worried about the risk, you should use a different password or even a certificate to connect to your Kali. And then even if someone can see that listening port, they can't connect. But if you have 4444 opening with that default Metasploit attack, that does open your machine to attack by anybody. And that's true of the real world too. Many botnets infect machines, and after that, they're easy for anyone else to take over. That's why the later generation of botnets will infect your machine and start a backdoor, and the backdoor will have a password to stop other criminals from stealing your infected machine. And in the case of the Mirai botnet, the Internet of Things, there was no way to lock anybody out because it was just a default telnet password in the hardware. So everybody that used the botnet, they just have another criminal come and steal your bots and use them for their attack, and steal your bots and use them for another attack. There was no way to claim your victims and hold on to them.
You know, it made me think about it. One of your classifications. It was a HELOC lab. And, you know, the names are not specific, like from a malware site. And so I got paranoid after that. I started kind of scanning my hard drive to see, okay, where's you? And so it just made you think more. It even made me think more about it.
Yeah, that's certainly true that there are some risks. And this is exactly what you need a security expert to help you with at a company, is to understand what the risk is. Now, in our case, we have a Kali virtual machine, which you're hopefully not doing banking on or storing credit card numbers on or anything. So even if somebody gets root on your machine, they can't steal anything important directly from that machine. And to attack your host, they would have to escape the VM, and that's pretty exotic. I don't think too many of us have to worry about that, but this is the kind of thought you have to do. Every machine has high security things that must be really well protected, and things that don't matter much that you don't have to protect. And you can make decisions for convenience because you know the risk is not too high or it's mitigated at another level. And that's just what everybody has to do. Anyway.
What about when you have a Windows virtual machine?
Yeah.
For some of the projects and some other classes, you ask people to shut down the security, the firewall and all that.
That's right.
They're more at risk.
They will be. And that's why if you take the Windows virtual machine that we set up to be the attack target, you shouldn't be doing shopping in that machine or saving personal documents in it or anything, because it is just a target machine, and we are going to infect it with malware and stuff.
I was talking about the host.
The host, well, I don't think I ever tell anybody to lower the security settings on the host, just on the virtual machine.
Yeah, I'm saying, so then host is not that much vulnerable.
Right. Yeah, you can leave everything on the host, the antivirus and the firewall and everything, and keep it reasonably safe. That's the main thing you do with virtual machines. You make your virtual machine vulnerable and attack it, but you keep your host relatively clean, although there is some risk to the host, even in doing that, if you're going to have a world that contains VM escape attacks. And now those do exist. They're not unheard of. Another thing which they were talking quite a bit about at IRCon I just went to was malware that notices it's in a virtual machine and doesn't run anymore. So you actually have to run special software to hide your virtual machine from the malware if you want to analyze it in the virtual machine. And that is something we've heard about for years. And we also said, oh, that's very rare. You'll never come across it. Well, now they're coming across that pretty often. So there will come a time, I suppose, when we see VM escapes pretty often. So, you know, right now we always this thing you say, oh, well, you know, that could be done, but you don't have to worry about it. Well, that's a temporary condition. You don't have to worry about it until enough of the bad guys learn this technique, then you have to worry about it. So you might want to think that, like I had students tell me they went to a bank and they were doing a hacking project on the bank at the work computer. And I said, I wouldn't do that. And he did, in fact, get in trouble for, yeah, that's why in general, you might want to consider that you shouldn't even be using a host that's full of all sorts of important things to do this. And I wouldn't worry too much yet, but there will come a time. And it just is a question of your tolerance to risk and your threat model. That's why some people have a special machine just for the projects, or they work in a lab or something because they're very concerned about doing it on their home machine. And I think that's unnecessary, but it's not stupid. You know, that is, they are correct that doing these projects, even in a virtual machine, places you to some degree of risk. Especially what I'm doing now. I'm doing forensic challenges where you're downloading malware and running it. The flare-on challenge, all that stuff you download will set off your viruses, and the fourth one is a malicious browser extension that I really don't understand. I'm trying to figure it out. And they said, you better do this in a virtual machine. You're downloading real malware. And that's true. I really don't know what it's doing. I really don't know how far it's going. And that's the case when you do malware analysis. You get threat samples and you don't know what you've got. So it is somewhat risky to work with. Anyway, let's talk about heap overflows. I went and got the very latest, in response to your, that thing where you showed me the latest version of, not this one, the latest version of Kali had a stupid change in the parameters in Metasploit just to break everything. So I got the latest version of Kali and make sure that what I'm doing works on the latest version. Well, the project we're doing today works just the same. But anyway, I'm trying to move up to make sure I have the latest version because Kali did change the -- payload options to -- list options, and they didn't even put in an error message to tell you this. They just give you an irritating message like invalid parameter or something that leads you no clue what the problem is. This is the thing about hacking tools. They are not user-friendly, and they're not maintained very well, so they will just change something that breaks everything and not tell you anything, not give you a help message, and leave you just sort of lost. You get used to it.
Well, I think part of it too is that I was a little bit complacent on the lab. It looked like I was doing it until I couldn't resolve part C.
Yeah.
I need to go back to see.
Yep. That's absolutely true. By the way, the NSA thing is going. The NSA challenge is up, so you might check it out. It's all about Ethereum this time. They have ransomware that infects you, and then you have to connect to an Ethereum blockchain to decrypt it, and you've got the network traffic and the binaries to analyze to decrypt this encrypted stuff. So it looks pretty good. I got started on it, didn't get too far yet, but it's on my homepage. And they don't, one thing about this one, they don't even tell you how long it's going to be up. So I don't really know what the rules are or anything, but I do see there's a bunch of colleges in, and a bunch of them have already done like the first 3 or 4 levels. So check it out if you're interested in cryptography and virtual machines and binary analysis. All good stuff. Anyway, I'm hoping to get my virtual machine connected. This one is, should have an address somewhere, 225.155. Okay, let me get it connected. SSH at 192.168.225.155. All right, good. So I've got a few slides, and then we'll do some heap exploits. Pretty simple stuff today, but it's important to know how to exploit the heap as well as the stack. So a heap is a different data structure. Now the stack is this special data structure we talked about that makes these frames, and it's last in, first out, specifically so it can be used for the calling of a subroutine and a sub-subroutine. And a sub-sub-subroutine is designed specifically for that job, where you go layer after layer, and then you have to return layer by layer. That's why it has this structure of frames and this idea that the last thing in is the first thing out. But there are other kinds of need for temporary storage in your computer that do not have that structure. For example, you might have a chat client or web browser that's processing network traffic, and it has to take a bunch of network traffic, store it somewhere, process it, and then when it's done with it, it wants to release it and make room for the next batch of network traffic. So that's the thing you might need a heap for. So the point of the heap is to store temporary objects and be able to allocate room on the heap and then let go of the room to make it available for reuse. So you can see it with info proc map in GDB. This will show you the memory map. You can also open your thing in Ollie debug and view memory map. It'll show you the same thing. There are various memory segments used by your code. Here's some libraries running up down here, and here's the main file here, heap 0, which has 3 segments that are labeled here. You've got the 2 segments here, and there's the heap. Someplace will be the stack. We have stacks down here, and the heap's up there. The heap, by the way, now in this case, they're similar size. Often the heap is bigger. Anyway, so the heap is a region set aside. By the way, Windows machines have many heaps. We'll get into that later. But anyway, the heap is a temporary place where data is stored. And the structure of a heap is a doubly linked list. There are several different kinds of heaps, but they all have this general property. You store data in chunks of various sizes, and then you have some metadata before each chunk. And the metadata has the size of the chunks and a pointer to the next chunk and a pointer to the previous chunk. So it is a linked list. And in Cisco routers, for example, they are very concerned with the integrity of the heap. Cisco routers are an interesting security case because they do not make any attempt to handle any errors. The only thing Cisco routers do is try to make sure everything is fine. And if anything is wrong, it just reboots the router because they are intended to be installed in a network closet and used for 20 years without any maintenance at all. So they want to just keep working no matter what happens. So if there's any kind of minor error in the traffic or the hardware or anything, so it crashes, it will just restart and move the packets again. So you can keep using it even when it's partially broken and it resets every 5 minutes because most of the packets still go through, and that's good enough. That's what it's designed for. So one of the things they have is a process called check heaps. And what it will do is go to the first chunk and follow the pointer to the next chunk and the next chunk and the next chunk. And when it gets to the end, it will just follow them all back, just making sure that all the pointers are okay. If this check heaps process runs every 2 seconds on a Cisco router, and if it finds that anything is wrong with the heap, it just erases everything, reboots the router, because that's how they are, because they don't really care about perfection. They just care about being up most of the time and keep the packets moving most of the time. And anyway, that's a test you can do on them. And the point here is if there's an overflow, if I'm able to put too much data in any of these, then I can overflow some of that metadata. And now it will be able to pass that test because I will change some of those pointers. And that's how we're going to take over the box. So here's a simple heap overflow. In this case, I make a data structure that stores a name and then a pointer. This doesn't allocate any space. These declarations up here, these are just declaring a data structure in C. So there's a thing called data that has a 64-character name followed by a pointer to a routine. And then I have a winner and a no winner here. I got this from some CTF. And I wonder if there's any way to fix the focus of this crazy thing. I can reach it, but standby input, yeah, looks like it's too smart to let me actually adjust anything. Anyway, just a moment, I won't try to do anything here. Nope, nothing, okay. Well, all right. Let me pause and see if I can, yeah, there's a panel there. Okay, well, guess I'll try it another day. Wonder if this junk does anything. Nope. All right. Guess we'll live with it. So anyway, there's a winner and a no winner function, and here's the actual name, which defines one of those data structures. And then it makes 2 of them. It allocates on the heap enough room for one data structure. And then it all it does in this case is make 1. Then it makes it point to no winner. Then you print something, copies the first argument into that structure, and then executes this function. This is very much like the very first thing you did, if you remember, when you had a string variable where you could have 40 characters, and the next variable after it was going to be executed as a bash command. And when you overflow to 40 characters, some of the extra characters would be run on the next line. That's what's going on here. I have a data structure, which is just going to print out the answer, and then after it, I have a pointer to the next routine. And I put in a pointer to the no winner function, and then I copy something from the user into it without checking the length. So if you can overflow it correctly, you can change that pointer so it points to the winner function instead of to the no winner function. It's a contrived example to be the simplest case I could think of a heap overflow. So you can view the heap, and the letters you put on the heap, and the pointer to that function appears here on the heap. So let me just bring this one up live. If I go here, here's my SSH into my Kali machine. And I could just as well be using a cloud machine. And if I go into my folder, all right, that's heap 0. So nano heap 0 .c is here. All right, get rid of the colors and make it big. So this is the data structure here, where I have 64 characters and then a pointer. Here's the winner and no-winner level, and here's the main. So at this point in main, I create room for the data and the pointer, and then I set the pointer to point to the no-winner function. Here is where I have the overflow. I'm going to take something from the command line and copy it on there without checking the length, and then go to what should be the no-winner function. So let's run this. If I run that, and I put in a small thing like AA, then it says level has not been passed. That's no winner. If I put in big things like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, let's put in a bunch of them. That's like 100. Now I get a segmentation fault, which is good. I've managed to confuse it. This is fuzzing. First I have it working, then I find a way to make it crash. So that means if I'm more careful, I can take control. And the way to do it, of course, is GDB on heap 0. All right, so let's do info proc mapping. And first I need to name one. I guess I have to run it. So let's do, let's run it. In this case, it's easy because it's going to, oh, that's right. It's going to ask, okay, it crashed. I can actually probably do it now. Info proc map. Yep, okay. So there's the heap. That's all I care about right now. 0804 D1000. So I'm going to quit from there. And then I'm going to run it again. And I'm going to give it a parameter. This thing needs a parameter to the command line, so I'm going to put in AAA. All right. Now, restart it. And it says level has not been passed. So I've jumped right through everything and hit the end. So now I got to put in a breakpoint. We've been here before. I can disassemble main. And when I do, I will see here it is allocating space. And here it is doing the string copy that's going to cause the overflow. And then it's going to come down and do some kind of call. So after the string copy is probably when I would like to break it. So let's break it here, main plus 120. Break main plus 120. That should do it. Now, if I just run it again here, and it hits the breakpoint instead of crashing after the string copy, unless I did that wrong. So let's take a look at the heap. So I can examine 120 hexadecimal words at the location of the heap. And so I see nothing but junk here. There's the 41. That's what I wanted to see. So here's the A's I put in. And here's a pointer right after them. So this data is under my control, and I can put in more and more A's until I eventually get here. This is probably the pointer to the next routine, 08, 04, 91 DB, and I can check that. I know that I should be no winner, so I can disassemble no winner and see if it starts at that address, 91 DD. And it does. So that address is currently no winner. So that's what's going to happen. If I continue, it's going to say level has not been passed. So all I have to do is the typical two-step we've always done. First, I gain control of the EIP, then I change it to a value I need to have in there. So I could, let's do an overflow. If I run this with a longer thing, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That might be enough. Okay, if I run it on that, and then I examine now the heap. If I go back to here, it was this address, 0804 D1B0, that contained the address I'm pointing to. So let's see what's in there now. Okay, here's all the data I put in, and there is D1B0. So it looks like I didn't have quite enough letters. See, my 48, 48, 48, 48 made it here. I need to do whatever I just put in, the next 4 bytes go in here. So I wasn't quite long enough, but I did accomplish my goal, which is to learn how to get there. So let's do this. There I am. I'm going to put in 1, 2, 3, 4 at the end of that, and that should hit the EIP. So let's start it again and examine the stack again, the heap rather again, and It looks like I'm still off by 1, 31, 32, 33, 34. Somehow I'm off by 1. That's the kind of stuff you always have to do. Let's have one more. So I need an I there. There. Now the 1, 2, 3, 4 should hit that pointer. Let's see if that works. And nope, looks like now I was off. I need 2 less now. Somehow I've had too many. All right. I could think it through a little better, but I really don't care. I just, trial and error is good enough for me. Let's run that. And yes. And that, and that. And now I'm hitting 1, 2, 3, 4. So that's the pointer. So I now know my attack. Here's my exploit. I want to send it that string right there, but the last 4 bytes should point to the no winner function. So I'm going to open up another window. I like to have one going to the into GDB and one not. So it's root at 192, 168, 225, 155. Okay. All right, so let's have user bin, get rid of the colors and make it big. Okay, shebang, user bin Python. And all right, that's the attack. I want to print that. Okay, and I'm going to call that start. And then I'm going to have EIP equals something here. And then I'm going to print start plus EIP. Now I need to know the values to put in there. And one of the values is this right here. No, that's not either of them. One of the values is, the only value I need is the address I'm going to. That's disassemble winner. Come on, come on. No, disassemble winner. Okay, this is where I need to go. That's the address I want to put in there. So let's put it here. This, I've gotten in the habit of doing this. It's not in your projects, but it's a good idea. I just paste in where I'm going because you often get the parameters backwards or something. It's good. This is my target winner at start of winner. There. So all I got to do is set E of equal to that. So that's what goes here. So it's everything backwards, backslash X 92, B2, backslash X 91, backslash X 04. There, that should do it. That attack should make me a winner. Let's see if that works. I need to make it executable. Okay, let's run it and see how it looks. That's what it should look like. And so if I run heap 0 on that, then I'm a winner, level passed. That's all. Because very simple, I had a structure that had a pointer right there, so I was able to overflow into a variable that was then used. And this, I hope, is easy to see. This is just following the same model as our first buffer overflow, where we had an unusual contrived condition to make it very easy to see what happens. I've just exceeded the space reserved for letters and able to leak into a space reserved for a pointer. And since computers don't know what they're doing, they'll cheerfully jump to something that was at one time interpreted as numbers and later on interpreted as an address. And they don't have any problem with that because they're stupid. So that's the game. You make a crash, do it in GDB, and then just need the right number of letters followed by the right pointer, and you can pass the level. So, the problem with the heap exploits, remember stack exploits, after we did this, where we overflow from one variable into another, we then just overflow from one variable into the metadata for the stack, which is the stored EBP and the stored EIP. The EIP is just sitting right there on the stack. So all you have to do is hit the right point and you gain control of the EIP. But that is not true of the heap. The heap does not have this return process where it takes data from a chunk and uses it to control the instruction pointer. It's all just data. So that's a problem. You don't have the EIP anywhere. In this particular case, we actually used something from the heap as an EIP, but that's normally not the case. However, you have something almost as good. You have an arbitrary write operation, and it happens when you free a chunk. Now, when you allocate space, that does not create a problem because you take a new slot on the heap, you start writing data to it. That's hard to exploit. But when you free a chunk, when I'm done using this middle chunk, and I call the free routine, what it has to do is first mark someplace in the metadata that that is available, and then it has to take the pointers going forward and change them, and the pointers going backward and change them. And what this means is it takes data from this chunk and uses it to determine what the address should be back here, and it uses both the content of that write operation and the address of that write operation come from data that was in one of these chunks. So if I'm able to overflow the chunks, then when a chunk is freed, I will find that there is a write operation that consists of data I control. And so I do not have direct control of the EIP, but I can write a word, and I control what I write, and I control where I write it. And as we know, if you can do a write, you can take over the machine because there are areas you can write to that will later end up in the EIP. We've done this before. We went to the global offset table, and we wrote there, and you could override pointer to a function. You could even write to a stack location when you return from a function, the destructors table, C library hooks. There's a bunch of places, exception handlers. There's a bunch of addresses which, when you write to them, will eventually end up in the EIP later. So it amounts to the same thing. All right. So let me ask a few cahoots about this, and then we'll go through another example or two here. Got them here. Let's see, no comments coming in or anything. Good, all right. So I just have to get my stuff to fill on the screen. Okay, cahoots. And we're going to need some sound, and I need to log in. Okay. And they should be my favorites. All right, wait, is that favorites? There we go. So this is 127, chapter 5. There's my favorites. Life is good. All right. Okay, good. What's happening? I'll get up a text document to record the winners in. All right. Save it somewhere. Whoa. Oh. All right, I'll give it a few more seconds. All right. So, which command moves the EIP to an attacker-controlled value in a Stack Overflow? All right, when you return is when you, that's what we've done right from the start. You overflow the values. When you return, it takes the stored EIP and puts it in EIP. So a value you control goes right in the EIP. All right. Which command allows direct control of the EIP after heap overflow? Okay, none of them, you do not get control of the EIP the way you do Stack Overflows. That's what's a little bit more difficult about heap overflows. All right, so how do you find the heap? Okay, info proc map, good. All right, so which command becomes an arbitrary write after heap overflow? Okay, it's the free that leads to an arbitrary write, which we're just about to go through. All right, which command reverse space on the stack? Okay, that's the normal one. Everyone got it wrong. When you refer, make a character with that statement there, that's reserved space on the stack. That's where local variables are stored. And which one creates a new chunk on the heap? Okay, that's malloc. Malloc allocates space on the heap and freeze it. The normal thing where you just declare a character, it doesn't say where it goes on the stack. All right, so let me record the winners, and then we will play with some more of these. Louise, and Delay, and Am are Unix. All right, and let's go here and take a look at the next one, which is heap one. So I got heap one dot C. Let's get rid of the colors. Okay, so this is from the same CTF. You can see the structure. So I have something up here called structure internet that just has an integer and a pointer to a string, and then char, a winner function, which it's never going to call. And it makes one chunk on the heap, and then it makes another chunk on the heap. And then it does a string copy of the first argument into the first chunk and the second argument into the second chunk. So I have two opportunities to overflow it, and then it prints that it's done, and it never calls the winners function. That's the point here. So if you run this, it wants two arguments. So it's heap one, and I can put in A and B, and it just says that's a rat vote. Nothing happens. So of course, to understand how it works, and I should be able to see the overflow. If I do heap one, and I put in a lot of A's, and then a B, then I get a segmentation fault. So there is a vulnerability here, and I can do some damage to the code. And to control it, I need to look at it in GDB, of course. So if I do this, and now I do, let's do disassemble main, and look to see, so here's allocating space for one and allocating space for another. And then down here, it's just returning. So there should be some string copies. There's string copies are where the overflow actually happens. So I think the thing I would like to do is stop it after this string copy and maybe again after that one, just so I can see what's happening. So let's do break main plus 148 and 175. And 175. Okay, and then I should be able to see what happens. So let's run it with A, B, 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 which should not overflow anything, and see what happens. So now I'm here. Now I want to look at the heap. So we do info proc map, and we can find the heap is here. So let's examine some space. Probably 60x might, oops, got to get out of here first. Okay, x/60x in the heap. Okay, so there's nothing here, so I got to look below. Let's just do more than 60, maybe 160. Okay, again, nothing, and again, nothing. Oh, there's my A's, 41, 41, 41, 41, good. So I found the A's. Strangely, I don't see the B's, which I find rather disturbing, but they can't be too far out of the way. Let's run a bigger attack. I'll go back up to here. Okay, let's put in more. All right, see what that does. Okay, if I examine the heap, oh, I know why. The first one was after the first copy operation, but the second copy operation had not happened yet. That's why I saw only my A's. So there's my A's, and the B's aren't there yet. I need to continue if I want to see the B's. And then I never make it to my second breakpoint. So the second operation failed, and it crashed inside the C routines way down here at string copy. Somewhere in string copy, it failed. All right, now this is because I overwrote some metadata, which was being used to create the next chunk, but I don't really need to analyze exactly why it crashed. I just need to find the instruction that crashed. Now it's died, so if I do info registers, I find the EIP way down here inside a C routine, but that's all right. I just want to see what instruction crashed. So I'm going to X2I EIP. I think that'll do it. Yes, it will. This shows you the instruction pointer. This is the instruction that caused the crash. Move EAX to EDX. okay? And EAX contains B's and EDX contains A's. The point is, this is what crashed, and it crashed at a move operation, both of which contain data I control. So that's all that matters. This is what I said. I now have a write operation, and I control both the data to be written and the address to write to. So I can totally take over the box now. I just have to get it under a little more precise control. So let's run it again and more carefully choose this stuff. So I'm going to do there, 1, 2, 3, 4, 5, 6, 7, 8. That'll probably do. Now I can tell what part of that controlled it. So I say yes to run it again, continue to get to the second point where it will crash. Now I do my examine the EIP. So it's moving EAX into EDX, and now info registers tells me EAX contains the B's and EDX contains 33, 33, 34, 44, which is 3344. So now I have my exploit. I'm going to copy this, and the 3344 is one of them, and the B's are the other. This is why I like to have two windows. Let's get out of here and make this, call this attack2. I'm only going to need one file. I need Python, user bin Python. Get rid of the colors and make it bigger. All right, now I'm going to put in, that's my string. So let's see, I want my, I'm a little unclear. All right, let me take a look at my instructions. A little unclear how I'm going to feed two parameters in to my program. Let me go back and look at my instructions for this one to make it a little smoother. This should be this heap overflow. Okay, so I've done all that. The thing that worries me is how I run it from my, there. Here's how I'm going to run it. Oh, like that. Okay, I can put two parameters in. I just wasn't sure you can put two parameters in that kind of statement, but you can. Okay, so this is what I want. I want to print this. Okay, and now I know the 3344 is what overwrites one of the values I need. So instead of 3344, I'm going to have value 1 and val space, and then val 2. Okay. And I'm being deliberately vague about those for right now because I find I always get it backwards when I try to think it through. I recommend trial and error. So let's set val1 equal to 1, 2, 3, 4, and val2 equal to 5, 6, 7, 8. There. There, that's my attack. And one of these will be written into the other as an address if I've done it correctly. So it's chmod plus x, att2, and if I run att2, it prints that junk out there, and that's right, none of these were non-printable characters yet. They're going to be later. But right now it's the 1, 2, 3, 4, and the 5, 6, 7, 8 that shall hit the two values if I've done this correctly. So I go here, and I run from att2. And I'll say yes. And I'll just continue. So let it crash. And now the instruction that made it crash is this one. And the registers at that point are this one. So EAX is 5, 6, 7, 8, and EDX is 1, 2, 3, 4. So I managed to hit both values, and the write operation goes from EAX into the address of EDX. So EDX, the 1, 2, 3, 4 is where the address goes. So now I'm going to modify my code. Okay, this is where the address goes. That's the address to write to. And the other one, EAX, is the data that's getting written to that address. So this is the data to write. So now I can do in a write operation, I can write anything I want, anywhere I want. Now I need to decide what to write and where to write it. Now, if we go back to disassemble main, as we've done before, I call malloc and malloc, then I call string copy and string copy, And then I call puts to print something on the screen. So I could overwrite the global offset table entry for puts, and that'll be an operation I control. So I think I'll do that. We've done this before. I'll exit this for a moment. If I do obj dump minus R of heap 1, I'll see the global offset table entries here, and you'll see that puts is there. So that's an address. If I write to that address, I will gain control of the EIP. So let's put that in my code. That's an address to write to, so that's what goes here. 2B, B2, 2B, B2, 04, 08. Okay, now the next thing is what to write there. And what to write there is the winning function. That's going to control the EIP, so I need to disassemble winner. Okay, this is where winner starts. So that's what I want to put in the other one. So my hope is I'm actually going to get it right this time. In the past, I seem to get it wrong every time and have to reverse it. Address of winner. So I would think that goes here. This might work. C2, 91, 04, 08. All right. So theoretically, I now have an attack that will overwrite puts with the address of my winner and print out the winning message. Let's see if it works. All I got to do is heap 1 at 2, and it did not work. I think that's the message I get when I did not win. And didn't crash either. What's that? I have a typo? Okay, good. There's a chat message. Maybe somebody else spotted it. 2B should be B8. Good, thank you. Good, thank you. Well, I've never made it in the first time ever. That's why I got used to this habit of having version 1, version 2, version 3. You know, even the simplest thing, if there's 2 ways to do it, I'll get it wrong at least once or twice. So C2, B8 instead of B2. Yeah, thank you. Good. Okay, B8. I'm surprised. Oh, it ran right through without changing because I wrote to some random value instead of that glob. I've changed one of the global offset table entries that I'm not using, like probably something like malloc that I'm not using again. That's why it didn't even cause a crash. Anyway, let's see if this one works. B8. Okay, good. And now I have a winner. Okay, good. So that was it. So the part that I always find disorienting about this is that it crashes inside a C library. So I keep thinking I've done something wrong, but that is normal. Inside the C library is where it tries to do a write to allocate the next chunk or to free the chunk, and it can't because the values are corrupt. Normally, I don't like to investigate crashes inside C libraries because I'm not usually looking for bugs in the compiler, but you're using the execution you need happens down there, but you're not finding the bug now there. The bug is in the data elsewhere, which doesn't lead to a crash until you're down in the library. Anyway, that's what I wanted to show you there. So there's a couple of them to get started, a very simple heap overflow and then a normal heap overflow with the overwrite. And then there's an extra credit one where you can get a remote shell because, of course, all we've done is run a little winner function. So I put up a server running one remotely, and you can get a copy of the code to play with locally. And when you get it working, then you have to upload a listening shell or a reverse shell or something and take control of my server. Or just execute bash commands. Once again, you have to write your name in a couple of files, and you'll end up on the winners page. And that you just have to add all the missing ingredients. I'll check and see if there's a problem. There should have been some winners there. But anyway, all right. I'll take a look at that and see if maybe my attack server is down again. It does get hacked all the time, strangely enough, and go down. So it requires a bit of maintenance. Anyway, anybody got any questions about anything? Well, that's all I wanted to tell you. I'll go upstairs and help anybody who wants help in the lab. There's no class next week. The next class will be in 2 weeks.
Can you give it a lecture or a workshop? Or what?
Yes, yeah, I'm doing a workshop down in Arizona, yeah. And so Liz and her team might be there competing in the CTF. That's not quite clear yet. Well, I don't know. I imagine it probably will be. All right, I'm stopping. Oh, if you want to tell me who you are to get points, Louise is the real name, but Daily and Remember Unix, we may not be able to figure out who you are. However, maybe that's going to be the name we'll find you under. I'll wait a few seconds and then stop the share. Oh, here comes the chat. Good. Not in your class. Okay, fine. That's okay then. All right, I'm going to stop the share. I'll see you folks in 2 weeks.
Just having problems in Project Core